In Physics 142, we're about ready now to start the next section in the textbook. And this also deals with wave properties, but special kinds of wave properties that happen when waves add up together to form a net disturbance. We just finished talking about standing waves. Standing waves occur when two identical waves travel through the same medium and move in opposite directions. What we're going to talk about now is called interference. And interference is a general term for dealing with the result when two or more waves travel through the same medium in the same direction. So mathematically, we can go through some of the same steps that we went through before and find out how to understand the answer. We'll also give some physical examples of how this interference phenomenon can happen. And there's some very interesting ones that we'll see, and we'll try to demonstrate some of these in class as well. One of the things that's interesting is this interference phenomenon happens both for sound waves and for light waves. And so the same basic models and mathematics applies to both cases. So let's jump in. Here we see two waves, and for simplicity, mathematically we're going to deal with waves that are moving just along the x direction. These two waves have the same wavelength, because k is related to the wavelength, the same frequency, omega, but the difference between them is a phase difference between the two waves. And so that delta could be any arbitrary value, but it just represents a shift for one wave with respect to the other wave. The standard mathematics of the superposition principle holds true. To find the net disturbance, or the net displacement, we simply add the two waves mathematically. And to do this, we're going to use the trigonometric identity that we used before. So simply adding them together and pulling out a factor of a for the amplitude doesn't do very much. But then, when we use this trigonometric identity, we see that we get twice the sine of half the sum of the two arguments, the two quantities in parentheses, multiplied by the cosine of half of the difference. And so, in just a few steps, you can see what happens is we end up with a result where the sine term has turned into a sine term down here that looks very much like one of the original waves. In fact, it's the sine of kx minus omega t plus delta over 2, which is really half of the phase difference between the two waves. But what we see out in front, acting as an amplitude, is that we've got 2a times the cosine of this delta over 2. So what does that do to this wave? What difference does that make? We can take a look at this a little more carefully and realize, as I mentioned before, that the sine term depends on x and t, and in fact, it's nothing more than a traveling wave, shifted a little bit, sort of right in between the two waves that added together to form this. But the amplitude function now not only depends on the amplitude of the individual wave, a, but it depends on the phase difference, delta. And so what we see is we get a traveling wave. When we add these two waves together, we get a traveling wave with the same wavelength and frequency, whose amplitude now depends on the phase difference. So it's natural for us to ask, where would we find the maximum amplitude? Under what conditions would we find the maximum amplitude? And then, under what conditions would the amplitude be minimum? So we'll call that 2a cosine delta over 2 a prime, because it functions like an amplitude. When we want the amplitude to be maximum, well, the cosine function will have to equal 1, because we know cosine goes back and forth between 1 and negative 1. So for maximum amplitude, cosine delta over 2 is 1. Therefore, delta over 2 has to have the values 0, right, pi, and technically here, cosine of pi would be negative 1, but all we care about is that the amplitude have its maximum value, whether that be plus or minus 1. So delta over 2 ends up being integer multiples of pi. so that if we multiply both sides by 2, delta is integer multiples of 2 pi. 0, 2 pi, 4 pi, 6 pi, and so on. And a nice compact way of representing that is to say that the phase difference, if we want the two waves to interfere and give a maximum amplitude, the phase difference will be an integer multiple of 2 pi. And we'll change notation here. Instead of using the delta, we'll call this delta phi, where phi is just the symbol that we used initially when talking about traveling waves to refer to the phase. So delta phi means a difference in the phase between the two waves. And so the phase difference, delta phi, will be 2n pi when the two waves have a maximum amplitude in their sum. Well, what about the case for the minimum amplitude? And it's just the opposite. Easily enough, we can see that we want the condition for the cosine of delta over 2 to be 0. Okay? So delta over 2 needs to be pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and so on, because the cosine of each of those angles is equal to 0. And multiplying through by 2, delta itself becomes an odd integer multiple of pi. All right? And a nice way to write that down is to write delta as 2n plus 1 times pi. So for n equals 0, delta is pi. For n equals 1, let's see, 2 times 1 plus 1, that's 3. So delta is 3 pi, which is the next term. N equals 2, we get delta equals 5 pi, and so on. So that's a nice compact way. And using, once again, this notation of delta phi to represent the difference in phase between the two waves, we have this condition. So, we've shown that when two waves traveling the same direction are added together, they form another traveling wave with an amplitude that depends on the phase difference. In the two extreme cases, when the phase difference is, and if I go back to the previous slide, when the phase difference is an integer multiple of 2 pi, then we get the maximum amplitude. When the phase difference is an odd integer multiple of pi, then we get the minimum amplitude. And so these two extreme cases correspond, in the one case, to so-called constructive interference. When the amplitude of the net wave is a maximum, we say that the two waves interfere constructively because they add together to give something larger, to give something that's absolutely the maximum it can be. On the other hand, when the two waves add together so that their amplitude is a minimum, we say that they undergo destructive interference because, in fact, the amplitude is 0. So the two waves add together under just the right condition to produce nothing as a result. They cancel each other out, and that's called destructive interference. The requirements for these two are summarized by the two equations that we just worked out. So these really are the take-home lessons for the addition of two traveling waves moving in the same direction. And we will use these in homework problems. What does this mean physically? Well, let's say that you had two speakers that were being driven by the same amplifier, and so they were playing music. Well, if those two speakers had different distances that their waves had to travel to get to you, the observer, then, under just the right situation, you might hear a very, very loud sound, which would be constructive interference. But then if you moved a short distance away to another location, you might be at just the right spot for destructive interference, and the net sound would be very soft. And so if you've ever experienced that in a room with speakers, you may have noticed that there are loud spots and there are quiet spots. And that's an example of constructive and destructive interference for sound waves. Some of your homework problems this week will look like that situation. Let's graphically just illustrate this. On the left-hand side, we see that we're adding together two individual waves that have a phase difference of 0. They're right on top of each other. In fact, you can probably not even tell that there are two waves there. But there's a red one and a blue one that overlap. And when we add them together, we get the same sort of wave, but now with twice the amplitude. And this is constructive interference. The sum is greater than either wave alone. But if we shift one wave by pi in phase with respect to the other one and add them together, if they started with the same amplitude, then they will add together to give 0. The peak of one is at the location of the trough of the other one, and the positive and negative values add together to give 0. Anytime we have constructive and destructive interference, we can be sure that this happens because we're dealing with waves. And the two cases are referred to using terminology that goes like this. If the two waves interfere constructively, we say that they are in phase because their phase difference is 0. If the two waves differ in phase by pi, then we say they're out of phase, or sometimes out of phase by pi. But if we just say that two waves are out of phase, generally we mean that they add together destructively. All right, there's another kind of interference that we can have for two waves, and this is the case when we have two waves that have slightly different frequencies. Not that their phase is different, but that the frequencies are different. And in the upper graph you can see that these two waves, the red and blue, started out right together in phase. In fact, the very first oscillation, you can't even tell the difference. But because they have slightly different frequencies, you can see that by this point here, it looks like they are exactly out of phase, because the peak of one is pretty close to where the trough of the other one is. And then after several more cycles, they come back into phase. So they start off together, right here in the middle, they're together again, right over here, they're together again. And if we look at the sum of those two waves, we see that on the plot below. And we see, sure enough, places where the net wave has a large amplitude, a maximum amplitude, where the two waves line up together. And so that's here, and then here, and then here again. And the spots right in between, where it looks like the red and the blue are shifted by pi with respect to each other, that's where they add up to give 0. And so what happens here, if we listen to the sound that comes from these two waves, and this phenomenon is most striking when we're dealing with sound, what happens is there are certain times where we get a very loud sound. That's the maximum displacement. And then there are times when we get very soft sounds, and they alternate, loud to soft to loud to soft. This kind of interference is referred to as beats. The beating is the change in the loudness as it goes back and forth, as the waves come in and out of phase repeatedly. And there's a very simple relationship for that rising and falling of the net sound, which is called the beat frequency. The beat frequency, the frequency with which they come in and out of phase, is simply the difference in frequency between the two waves. That's all there is to it. Now, if we want to see visually what's happening, we've already looked at the mathematics when we've got interference from two sources. But if we want to see what's happening graphically, let's look at the situation this way. Imagining that we have two sources, S1 and S2, of waves, and these could be loudspeakers that are being driven by the same amplifier, and so they're playing music that's carried by sound waves, and it has to go from each source, S1 and S2, to the observer at point P. And if the path that they have to travel to get to point P is exactly the same, and if the two waves begin with the same phase, you can see right here that where they're at the individual sources, the phase is exactly the same. That if they travel the same distance to get to point P, then they will still be in phase together at that point, and we will see constructive interference. By contrast, if the path that one of them has to travel is a little different than the other one, then even though they start out in phase, when they reach point P, you can see here what happens is one of them is at a peak. The wave that goes from S1 to P is at a peak right here when it gets to point P, while the wave that goes from S2 to P is at a trough. And the peak and the trough will add up to give 0, and now we know that that's destructive interference. And so these are the two special cases. We can certainly have something in between the two, but these are the two most striking ones. And if the sources of waves were sound waves, this would be on the left a very loud interference, constructive interference, and on the right it would be destructive, so this would be a location of very soft sound. Now there's special requirements to observe this kind of interference. So we've mentioned one of these already. We've assumed that the waves have the same wavelength, because if they don't have the same wavelength, then this sort of addition of the waves will occur in a very complicated way, and we won't really be able to see this sort of interference. But the other one that's required to observe interference is that the sources of waves be coherent. Basically, what we require is that their phase relationship stays the same, so that if the two waves from S1 and S2 start out in phase, they stay in phase. They don't shift with respect to one another along the way. And the simplest way for that to happen for coherent sources is for the two sources to be connected through, let's say, the same amplifier for sound waves. Or if these are light waves, we require that they both come from the same source of light. And we'll show how to do that a little bit later. So here's a case where we can see more clearly why you might have constructive or potentially destructive interference when waves come from two different sources to reach a common point. Here, in this larger diagram, we see waves that come from S1 and S2. When they get to point P, they're in phase. They add up to give constructive interference because their peaks are both at point P. Well, what's different about these two is the extra distance the wave had to travel starting from point S2. And here's the key. If the wave has to travel an extra distance, which is a multiple of the wavelength, an integer multiple of the wavelength, then when it gets to this spot here, so that the rest of its path is going to be the same distance that the wave travels from S1, then they're going to interfere constructively. If that extra path difference is an integer multiple of the wavelength, then we will see constructive interference. And the symbol that our textbook uses for this difference in path is delta R. Delta meaning change, R meaning the distance it has to travel. So if delta R is an integer multiple of the wavelength, then sure enough we get constructive interference. The other possibility, which is not shown here, but is easy enough to imagine, is what if that path difference instead was 3/2 of a wavelength, or 5/2 of a wavelength? Then the two waves would be starting out at different points in their phase, and when they reach point P, they would interfere destructively. So if delta R is a half integer multiple of the wavelength, 1/2, 3/2, 5/2, so on, we see destructive interference. As we said, there's two ways of making sure that the sources that you have are coherent. If the sources are sound waves, we just make sure the two speakers are driven by the same amplifier. One way to do it with light waves is to make your sources be slits in an opaque screen, so that the light that goes through those slits comes from the same original light source. That will make sure that the waves, when they enter those two slits, actually have phase relationships that stay the same, because they'll be coming from the same original source. So that's what we mean by coherence between sources, that their phase relationships, whatever they are, that they stay the same all throughout their motion. Okay, So that's good enough as an introduction to this topic of interference. And in class, we'll go over an example that looks like this. That deals with two speakers being driven by the same amplifier and emitting waves that are in phase. And that's what we mean by coherence. We're given the frequency, the speakers are placed in a certain location, and an observer 75 meters away is listening to the two speakers. And so we'll imagine what can happen if the listener initially listens to the sound coming from those speakers when they're in the same place. And then what might happen differently if one of those speakers is moved so that the sound coming from the two speakers to the observer travels different distances. That's where things get interesting. So, hope this is a good introduction. Please look over your textbook because this information is presented in a little bit more detail. And next time in class, we'll work on this and other examples.